This video is going to be problems 6 through 10 on the Introductory Ksp problems. The other video I had problems 1 through 5. So number 6 is right here. We're mixing 50 milliliters of iron nitrate with 35 milliliters of this molarity sodium carbonate. Again, iron nitrate has nitrate in it, so completely soluble, no Ksp value, have an infinite Ksp value. And sodium carbonate has sodium in it, so it's completely soluble. And wants to know, will they precipitate form? So this is one of those things where we got to figure out which thing will be the precipitate, and then figure out what are the concentration of those ions, and is the value above K or below K. So we'll call that Q when we're doing this. So if we say, okay, we have this beaker here, we've got 50 milliliters of iron nitrate, so that means we've got some iron ions and some nitrate ions. 35 milliliters of that molarity sodium carbonate, so we got some sodium ions and some carbonate ions. And together now, 50 milliliters and 35 milliliters, they're in 85 milliliters of solution, which will make a difference in the concentration of them. Well, nitrate and sodium never form precipitates, so nitrate and sodiums are always soluble, never form precipitates. Iron carbonate can be a precipitate, and the Ksp of iron carbonate is, I don't know, just a second, 2.1 times 10 to the 11. So we need to figure out, if we plug into the Ksp expression, iron ions times carbonate ions. So if we put those values in here, we got to figure out, is it bigger than this value? If it is, precipitates formed. If it's right at this value or below, those things can dissolve, no precipitates formed. Well, we can't just plug in this molarity and this molarity, because we've now mixed the two solutions together, which changed the concentration of those things. So we got to figure out how many moles of iron ions are there here, divided by this liters. How many moles of carbonate ions here, divided by that liters. So if we go concentration of iron ions is going to be, we had 0.5 liters times, every liter contains 2.1 times 10 to the negative 6 moles of iron nitrate, which would be moles of iron ions. So we get that is 1.05 times 10 to the negative 7th moles of iron divided by 0.085 liters, because it's now in that much solution. And you get 1.24 times 10 to the negative 6. That's a concentration of iron ions. Get our concentration of carbonate ions. So again, get moles of them. We have I should have been 0.05 liters, sorry, up here. 0.035 liters. Every liter contains 3.7 times 10 to the negative 5th moles. That's the molarity of it. And that is carbonate ions. So we get our moles. 1.29 times 10 to the negative 6 divided by 0.085 liters that's in now, and we get 1.52 times 10 to the negative 5th. So we have our two concentrations in this. We obviously have some sodium ions and nitrate ions floating around with them. Does not affect it. So plug those in. We'll call that Qsp and see if it's right. See if it equals to Ksp. So plug in iron's concentration 1.24 times 10 to the negative 6 times carbonate's concentration 1.52 times 10 to the negative 5th. When we do that, we get a Qsp of 1.89 times 10 to the negative 11th. Well, that value is smaller by a little bit than the Ksp. So this amount of iron and this amount of carbonate can dissolve. Okay, because remember, this would be the maximum amount these can multiply to. We're a little bit below, so that is less than the Ksp, so no precipitate would form. You would not get any solid iron carbonate in the bottom of that. One of the longer, tougher problems definitely there. Number 7, figure out the solubility in grams per liter of magnesium hydroxide Okay, now usually we've been figuring out the solubility in water. This time we're figuring it out in a solution that already has one of those ions in it. So that will affect how much can dissolve. So there's our Ksp value. Again, we're figuring out the solubility in grams per liter if we are in a 0.25 molar sodium hydroxide solution. So if we write our Ksp expression, Ksp equals concentration of magnesium times concentration of hydroxide ions squared. Well, we're not dissolving this in water. If we were, we'd put in an x, a 2x, and we'd square it. In this case, we're dissolving it in 0.25 molar sodium hydroxide. So that means you have 0.25 molar sodium ions, 0.25 molar hydroxide ions. So we're going to put in 0.25 right there for hydroxide, and an x right here, and figure out how many magnesium ions can be in there with that. And so that'd equal to the Ksp. Now, people usually ask, does this need to be 1/2 x or anything like that? No, it's just x. If this concentration is here, we already know that's 0.25. We're going to figure out what is the max amount of this we can dissolve. So square 0.25 divided over to this side, and our x value is 1.42 times 10 to the negative 10th moles per liter. So that'd be concentration of magnesium, which would be the same as the concentration of magnesium hydroxide. So that is magnesium hydroxide. That is the maximum amount of this you could put in a solution that already has this much hydroxide in it before precipitate starts to form or solid starts to form. Well, I want to know it in grams per liter, so we're going to go times the molar mass. Mole of magnesium hydroxide is 58 grams. So that's the maximum amount. It's not very many grams. It's the most you can dissolve in a 0.25 molar sodium hydroxide solution. Now, you could put a lot more in water because you would already have those ions in there, which make you reach the Ksp value sooner. Number 8, we got a 15-gram sample of sodium iodide dissolved in water. Again, sodium iodide would be completely soluble. The solution is then saturated with lead 2 iodide. So think about this. We've got some sodium iodide, 15 grams of it dissolved in water. And then we start adding in some PbI2, which is going to add lead ions, iodine ions. We already have some iodine ions in there. Figure out the concentration of the lead and iodine ions. So let's figure out 15 grams of sodium iodide. Let's figure out how many moles that is. It's 150 grams per mole. And we are in 0.25 liters of solution. That'll tell us the molarity of it. So that is the concentration of the sodium iodide we have there, which means that the concentration of sodium ions is 0.4 molar. The concentration of iodine ions is 0.4 molar. So we know the concentration of iodine ions will be 0.4 molar. Now if we start adding lead iodide in here pretty soon, we're going to get a precipitate pretty fast. So if we figure out the concentration of lead ions that could be in there, we're going to say Ksp equals the Ksp expression. And the Ksp value 1.4 times 10 to the 8 equals x for lead. How much lead can we put in there? Since we already have 0.4 molar. So square that, divide it over our x. So that is the most lead ions you can put in there if the iodine ions are 0.4 molar. You can't put any more of that in there. The rest will undissolve, be at the bottom of it. Number 9. Maybe run out of time on my video here. I have to put just number 9 on here. Magnesium nitrate is added to a 0.0037 molar solution of sodium carbonate. At what concentration of magnesium does a precipitate start to form? So think about this, we're adding, so this, like we had similar, we're adding magnesium nitrate, which is completely soluble, into some sodium carbonate. So again, sodium and nitrate never form precipitates, that does. So it's telling us we know the concentration of carbonate is 0.0037 molar. We don't know any other concentrations though. At what concentration of magnesium does a precipitate start to form? So the Ksp of magnesium carbonate is 1 times 10 to the negative 5th. So we're going to say Ksp equals concentration of magnesium ions times concentration of carbonate ions. And the Ksp is 1.6 times 10 to the... So put in an X for magnesium. We know the concentration of carbonate ions is 0.0037 molar already. So just divide this by 0.0037 molar. And our X value is 0.0027. So that is the maximum amount of magnesium ions you can put, 0.0027, in with this carbonate before you get a precipitate. So anything greater than this, okay? Anything greater than 0.0027 molar will cause a precipitate. This is the exact amount that will dissolve with this. Enough magnesium nitrate is added to make the concentration of magnesium to be 0.0045. So now they're saying they're making this concentration 0.0045. What percentage of the original carbonate ion would precipitate out? What percent is still in? So we can figure out, let's figure out how much carbonate ion would stay in there. So if we say let's figure out if magnesium is 0.0045 molar. Let's figure out what that can be. It's equal to Ksp 1.6 times 10 to the negative 5th. So this will tell us the maximum amount of carbonate ion that will dissolve with this molarity of magnesium ion in there. And X, which is our concentration of carbonate ions, is 0.022 molar. So again, that is the maximum amount of carbonate ion you can have with this much magnesium that's already in there. So let's figure out the percent that dissolved. Okay, or percent dissolved or percent precipitated out. Would be, we have, this is the amount that's dissolved, so 0.0022 out of the original 0.0037. So this is the amount dissolved out of the amount that was dissolved originally, equals 59.5% is still dissolved. That means the rest precipitated out. So 40.5% precipitated out. All right. That's going to be the last problem I can put on this video without going over the 15-minute time limit. I will post number 10's answer with the answer key to this.